In this tutorial, we are going to talk about electric field and electric forces practice questions. So I've got a number of questions with me here. The first question is, what must be the charge, which is the sign and the magnitude of the particle of mass 1.43 grams, B, for it to remain stationary when pressed in a downward direction, electric field of magnitude 660 Newton per Coulomb. Then part B, what is the magnitude of an electric field in which the electric force on a proton is equal in magnitude to its weight? So let's first start with part A. Now we have been given the mass. So we can clearly see that we have the mass. Now this mass which have been given here is in grams. We have to convert this from grams to kgs. Okay, so there we go. This is the same as just times 10 to the power negative 3, or just divide it by 1000. So this is now in kgs. What else do we have? We also have the electric field, which we've been told that this is 660 Newton per Coulomb. Okay, now the question is saying, what must be the charge, or what must the charge of a particle 1.43 grams be for it to remain stationary when placed in a downward direction electric field? Now the electric field is going downward direction. That is our electric field. Okay, now let's say the charge is here, but we don't know the sign of this charge, but we have been told that this charge is at stationary. Okay, so now when something is at stationary, it is in free fall. What we need to remember is that there is always the force of gravity which is trying to pull this object down. Now if there is force of gravity, for it to remain at stationary or in stationary, meaning that the electric force has to be in that direction, so that the mg and the electric force should be the same, then the net force will be 0. That charge is going to be at stationary at that point. Okay, now let's think of this. We have been told that the electric field is moving, is going downward, and one thing we have to understand is that we are trying to find the magnitude. So if it is at stationary, the summation of all the forces in y direction, in this case we have got the electric field, then which is pointing upward, I'm going to assign it as a positive. Then I also have the mg pointing downward, which is going to be minus. According to Newton's second law, since it is at stationary, it is not moving, the net force is 0. So I'll replace that with a 0. Will be the electric force minus mg. I can shift this to the other side. I'll say that mg is equal to Fe, or Fe is equal to mg. I'll leave it there. Now one thing we have to understand is that the electric field is also given by the electric force divided by the charge. Okay, so now here we have been given the electric field, but we want to find the charge. Okay, so meaning I have to find a way on how I'm going to eliminate this electric force, because I don't need it. I don't have any information about the electric force. Let's make the electric force as a subject of formula. So if I cross multiply here, I'll find that electric force will be equal to the electric field times the charge. So I can replace where there is electric force with the electric field times charge. So here I'm going to replace with this is equal to mg. My goal is to find the charge, and I have now everything. I can just divide both sides by electric field, even here by electric field. So charge will be given by mg divided by E. Okay, let's go ahead and now plug in the values. So have a charge will be equal to the mass is 1.43 times 10 to the power 3 times 9.8, what that is G. Then now electric field is 60. So Q will be equal to 1.43 times 10 to the power negative 3 times 9.8 divided by 660. So the electric charge which I'm getting, I have to put it in scientific notation. It is 2.12 times 10 to the power negative 5 Coulomb. That is my charge. Now if I want to make this, I want to put the answer, I want to report my answer in microcoulomb, I'm supposed to do times 10 to the power, I'm supposed to do times 10 to the power 6. So I can also say times 10 raised to the power 6, that meaning that my answer will be in micro or in microcoulomb now in that case. Okay, so my answer in microcoulomb is going to be my Q, I can put it here, will be equal to 212.33 microcoulomb. So if you want, you can report your answer in microcoulomb or just the coulomb the way it is here. It's okay. Okay, so that's the magnitude of this charge. Now the question here is saying we need to find the magnitude and the sign. Okay, now how can we find the sign here? Let's think of this. Finding the sign here, we need first to think of the electric field and the electric force. So we are saying that electric field is going in that direction, and one thing we have to remember is that the positive charge will go in the same direction with the the electric field. Then the negative charge has to go in the opposite direction. Okay, so now one thing we have to remember is that the electric force is in that direction. Then here we have mg. Now that now we know that the electric field is going downward. If the electric field is going downward, meaning that if we're talking about the positive is also moving in the same direction. Okay, so if the positive charge, if we have the positive charge, definitely we expect that one to start now going down. Okay, now since we know that where the electric field is going, meaning down here it is negative, the surface here is negative charged, so this is negative charge, down part here the surface is negative charge, that's why the electric field is going downward. So if I make the charge to be positive, definitely the meaning that it's going to be attracted is going to be moving down. But if I make this charge to be negative, okay, let's think of this. If I make this charge to be negative, meaning that this negative and the negative which is down here, they are going to be repelled to each other. Therefore, it's going to remain at stationary. So the charge has to be negative so that it should be repelled with the negative which is here. The reason why we are thinking that the surface is negative, but it's just because the electric field is also pointing downward. Okay, the electric field is pointing downward, meaning that that's where the negative is. Okay, so now one thing we have to understand of this, when we're talking about the electric field, one thing we have to understand is that if you have got a negative here, okay, the electric field will always move toward the negative. So this is the electric field. Now since this electric field is coming down, meaning that where it is going, it is negative, the surface is negative. When we have got a positive, it will always run away from the positive. That's what we need to know. Okay, so it is going toward, meaning that where it is going is negative. So we have been told that the electric field is going downward, meaning that downward there it is negative. So the charge has to be negative so that it should remain stationary. The negative and negative should repel each other. We can't make this charge to be positive. Once we make it to be positive, it's going to be attracted to downward as well. But we want it to be suspended in air, so it has to be negative. So the sign is negative and the magnitude is 2 2.12 times 10 to the power negative 5 Coulomb. We are done for part A. Now we go to part B. So part B is saying what is the magnitude and what is the magnitude of the electric field in which the electric force on a proton is equal to the magnitude of its weight. Okay. Now here we're talking about a proton. So we need to know the mass of the proton. Okay. The mass of the proton, one thing we need to know is 1.67 times 10 raised to the power negative 27 kgs. That is the mass. Then what's the charge? The charge of the proton is 1.6 times 10 to the power negative 19 Coulomb. Then we know that when we're talking about it is also suspended in air. That's what we've been told. Meaning that here you have mg, here you have the electric field going in that direction. The summation of the forces in y direction will have this minus mg. So we end up having 0 to be equal to this. We'll have the same thing. So we'll have F is equal to mg. Remember that electric field is given by the electric force divided by a charge. And our goal is to find the electric field. We are not interested in the electric force. So we'll make electric force here as a subject of formula. It's going to be electric field times Q. So I'll replace this with the electric field times Q. Our goal is to find the electric field. We divide it by this. So this will be equal to mg divided by Q. Now we have everything here, guys. So this will be equal to, the mass is 1.67 times 10 to the power 27 times 9.8. Divide this by the charge, 1.60 times 10 to the power negative 19. So the electric field for this proton is going to be 1.67 times 10 to the power next 27 times 9.8. I divide it by 1.60 times 10 to the power negative 19. So I'll put it in scientific notation. The answer is 1.023 times 10 to the power negative 7 Newton per Coulomb. That is my electric field. So that is it for this question. So now let's solve this interesting question and electric field. So sometimes I always tell you to say it's very important for you to understand the question before you even start solving. So here's the question. An electric field of 100,000 Newton per Coulomb causes the 5 grams point charge to hang at 20 degrees angle. What is the charge on the ball? Okay, so now think of this. Let's first understand the question. We have got electric field which is making this 5 gram charge, or we can say a ball, to be pointed at an angle. Now let's think of this. So if something is pointed at an angle, let's say this has been pointed at an angle, and here is the angle here, and here is our charge, which we don't know the charge definitely, and the angle is 20 degrees. As it is swinging, there is a force of gravity which is pulling this board down. Okay, so that force, I'm going to say it is mg. Okay, now we are saying that this electric field, it is causing this ball to hang at an angle. So for it to cause this ball to hang at an angle, meaning that it is moving in that direction, meaning that is our electric field, which is 100,000 Newton per Coulomb. Why are we saying this? Because it can't go in this direction, because we have been told that this electric field is the one which made this ball to hang at an angle, meaning that it was pushing it in that way. That's the reason why the electric field has to go in that direction. It can't go toward west, because if we are to say it's going toward west, meaning that we have to arrange our free body diagram to be in this manner, then it can go in that direction. We should definitely get the same answer still. Okay, so that's why when you understand the question, especially physics, it will be very much easy for you to know what we are talking about. Now let's come up with a free body diagram, the forces which are acting in this case. One thing we have to remember is that where the electric field is pointing, that is where the electric force is going. Very, very important in this case. Okay, so now let's have a free body diagram in this case. So here is our ball. So any force which is supported by the loop is what we call the tension force. So in this case, that will be my tension force. I'll call it Ft. Mg is here. Now this tension force is acting at an angle, so we know that we'll have that, meaning that this is Ftx and that is our Fty. So this is the same as I've just done it like that. So this Z which is being formed there, the angle here is the same as the angle there. Therefore, here the angle is 20 degrees. Meaning that using SOHCAHTOA, my Ftx will be Ft opposite sine theta, and my Fty will be Ft cos theta. As simple as that. So now it's now swinging. We don't have the acceleration, the net force is 0. So there's the summation of all the forces in y direction. We have Fty pointing upward minus Mgy. This minus is for Mg because it's pointing downward. So here 0, since it's not moving. This is Ft. Ft can be replaced, Fty can be replaced by Ft cos theta minus Mg. I shift this to the other side, same as I have got Ft cos theta is equal to Mg. Our goal is to find the charge. Here I don't have any I've got the tension force and I'm not interested in the tension force. Let's call that one as equation 1. Let's work around with the forces in x direction. The summation of forces in x direction, we have got the force which is moving in this direction, which is the electric force. So I'll put that minus, there is Ft moving now in that direction. Now the tension force, the arrow here, when we go back to vectors, the arrow is there. That's why here is pointing up, then it has to go there. So the arrow for Ftx is pointing toward the negative x-axis. That's why it's negative Ftx. Since it is not moving, this will be replaced by 0. So we'll have this minus Ftx is Ft sine theta. If I shift that to the other side, it's the same as Ft sine theta is equal to Fe that. Sometimes you're already confused. Why am I not shifting this to the other side? It's the same. In fact, here I've just shifted, but in a case of this, here I've shifted this to the other side. That's why it's like that. But here, why didn't I just shift this to the other side? It's the same thing. I shift this to the other side, it's the same as this. Okay. Then now I'll call this equation 2. Now let's remember this. These equations which we have just come up with here, one thing we have to remember, want to find the charge. There is no equation which is giving us anything to find the charge. So we should remember that electric field is also given by the electric force divided by a charge. So we can make electric force as a subject of formula. So it will be electric field times a charge, meaning that where there is electric force, I can replace it with electric field times a charge, because I have the electric field and I want to find the charge. So this guy here is going to be replaced by this guy. So to create space, let me get rid of this. So the first equation, we are saying ft cos theta is equal to mg. Then the second equation is ft sin theta is equal to electric force, sorry. Now let's get rid of this. I want to create space here. Now we are saying that where there is electric force, we'll replace it with electric field times the charge, meaning that ft sin theta will be electric field times the charge. Our goal is to find the charge. How can I eliminate the tension force? Let's make the tension force as a subject of formula in the first equation. In the first equation, which is ft cos theta is equal to mg, let's divide both sides by cos theta. Even here, cos theta. What do we expect? These will cancel. We will have ft will be equal to mg cos theta. So where there is ft in this second equation here, I will replace mg divided by cos theta. So I'll say mg, I've got divided by cos theta, then times sin theta is equal to eq. So what is sine divided by cos is tan. So we have mg tan theta is equal to eq. Okay. Now we have everything. We have got the angle, which is 20 degrees. We have the electric field. We want to find the charge. Divide both sides by E. Both sides by E. Therefore, our Q will be mg tan theta divided by E. Now, one thing I want you to understand is this. From these formulas, from this formula here, before we even continue, let me explain something. From these two formulas here, the first formula and this one, when I combine them, I get to find this. I get to have this one. Mg tan theta is equal to EQ. Here I can find anything which I want. I can find the mass, I can find the electric field, I can find the Q. I can also find the electric force if I've been asked to find the electric force, because I will replace this with electric force. You see? So anything you're going to be asked here, as long as you reach at that point, you see what is missing. Then start now substituting. Plug in the values, see what is missing, find it. As simple as that. So in this case, let's go ahead and see what our charge is going to be. The mass is 5. Now this 5, we convert it to kgs, is divided by 1000, or just say 5.0 times 10 to the power negative 3, then times 9.8 times 20 degrees divided by 100,000. What is our Q? So our charge will be equal to, if I get my calculator, 5.0 times 10 to the power negative 3 times 9.8 times 20. The answer is divided by 100,000. So I have to put it in scientific notation, which is 1.78 times 10 raised to the power negative 7 Coulomb. That is the charge. Now, if I want to leave my charge in microcoulomb, I need to do times 10 raised to the power 6. Meaning, my answer in microcoulomb, it will be 0.18 microcoulomb. So you choose. It's either you report your answer in this, in coulomb, or in microcoulomb. Both answers are correct. As simple as that. So let's talk about the question 3, which is coming from an infinite long line of a charge. So the question is saying an infinite long line of a charge has a linear charge density of 8.00 times 10 to the power negative 12 centimeters per meter, or Coulomb per meter. A proton is at a distance of 19 centimeters from the line and is moving direct toward the line with a speed of 1200 meters per second. How close does the proton get to the line of a charge? Okay, so now this topic is very interesting. So let's first come up with data. So we have been told that we have got the linear density, the linear charge density, which is represented by lambda. So we have been told that is 8.00 times 10 raised to the power negative 12 Coulomb per meter. What else do we know? We have been told that the proton is at a distance of 19 centimeters, meaning that is our initial distance. So our initial distance is 19.0 centimeters. Now we need to find the final distance, which we don't know. That's the question now. How close does the proton get to the line of the charge? Meaning that's the final displacement, the final distance. So we have been told that the velocity, now this velocity initially is the initial velocity. So the question is, moving direct toward the line with a speed of, so it was moving with a speed of that. So the speed now is 1200 meters per second. So we are saying that how close does the proton get to the line of the charge? So when the proton gets to the line of the charge, it will stop moving. Now we want to find the final distance at that point, meaning that the final speed is 0. Okay, now there are some few formulas which we need to know for us to work out any question for an infinite, okay, of a charge. Now these formulas I think is going to be a bit complex if I can show you where they are coming from, but I'm going to give you such that whenever you see a question asking about the infinite, you'll be able to use the same formulas and you'll be able to find what is missing. Okay, so the first formula which we have to know is the potential energy. Now the potential energy, when we're talking about the electric force and electric field, it is given by, the potential energy is given by the charge times the voltage. So this is the charge and that is the voltage. It's not the velocity. This is not the velocity, but it's the voltage. Okay, that is one formula which we need to know. Another formula now we need to know that we always have conservation of energy. Now conservation of energy can neither be created nor destroyed, but it can be transformed from one state to another. So what we know is the initial mechanical energy should be equal to the final mechanical energy. So we are going to have the kinetic energy. Okay, since it is moving, we have got the velocity. We also have the potential energy because we have got the charge and the voltage. Okay, so we'll say the kinetic energy initial plus the potential energy final, or initial, should be equal to the kinetic energy initial final plus the potential energy final. Now one thing we have to remember is that kinetic energy is always half mv initial squared plus the potential energy we're talking about here is not mg, it's not mhg, where we say mass times gravity times h, no, but it is the charge times the voltage. So I'm going to say the charge times the voltage. Now which voltage? The voltage initial. Okay, even here is going to be half mv final squared plus the charge, the voltage final. Now this, let's not confuse ourselves here. Here I'm using this is the velocity, but this is the charge, the voltage, okay, which we are talking about here. For the potential energy is the voltage and not the what, the velocity. So now one thing we have to remember here, we have been told that since we are saying that as it is getting closer to the proton, the line of the charge, meaning that the final velocity is 0, we don't expect to have that. So we have half mv final squared plus, this is the qv initial, that is the voltage, then again qv final. So I'm going to leave this formula here, I will leave it there. Now I'm going to get it here and put it down here. Let's get rid of this. Another interesting formula which you need to know when you're dealing with the infinity of a long line of a charge is this one, the voltage difference. So the voltage difference is given by the voltage initial minus voltage final should be equal to the linear charge density divided by 2 pi absolute. So then this is given by ln RF divided by R initial. RF is the one we are trying to find, this one here. Again, this formula, so now here only three important formulas you need to know. The formula for the potential energy, which is given by the charge times the voltage, the formula for the conservation of energy, and this formula for the voltage difference. Now after doing this, one thing we have to remember is that we don't have this, but now we don't have voltage. We have not been given any voltage here, but I can make voltage as a subject of formula from this equation. Okay, so let's just get this equation here and make voltage as a subject of formula. How? So we have half mv final squared plus qv initial will be equal to qv final. So what I'm going to do now, I'm going to shift this to the right hand side. So it will be what? It will be half mv final squared. Oh, it should be initial because final has already gone. What I mean here is this. Let me show you. It was initial. This was supposed to be initial. So even here supposed to be initial. Let me just write it. So the formula is half mv initial squared plus half or plus the charge plus voltage initial is equal to the charge voltage final. I'll shift this to the right hand side. I'll have half mv final initial squared should be equal to this and that. Now remember that what we have here, we are trying to make this v initial minus v final as a subject of formula, which is the voltage initial minus voltage final as a subject of formula. I can make here now I want to make v initial minus v final, meaning I can factor out negative q. So let's do this. Let me first put this one here. I'm going to write this like that. Then this will have this. Okay, now I can get rid of this. Let's make negative q as a subject of formula. So negative q will be equal to, meaning here is going to be negative v final, so that negative and negative should give me the positive, meaning I go back to that. This is going to be plus v final like that is equal to negative half mv like that. After doing this, the next thing what I'm going to do is I will divide both sides by negative q. So if I do that, it's the same as I start writing this. Since it's positive, then I say v, then this. It's the same thing. I will divide it by q now. Here I'm supposed to put just 1. So it's half mv1 I squared. I divide by negative q. So I will remain with this negative half mv initial squared divided by q like that. Now that I have this, what I have to do is, since I don't have voltage, I'm going to replace this with that. So let's go ahead and do that. So that is going to be replaced by half mv initial squared divided by q should be equal to the linear charge density 2 pi absolute, then R final divided by R initial like that. And our goal is to find the R final. Now we have everything here. So this absolute is just basically the constant. it is 8.85 times 10 raised to the power 12. And you're going to be given always, whenever you see this question, just look the last paper or the last page of the question paper, you'll be given this constant. Then again, when we're talking about the charge, we're talking about the proton. Okay, so the charge of the proton is constant as well, we know it already. So these I'm going to put them where the charge of the proton is 1.67 times 10 to the power negative 19. That's the charge. Then the mass of the proton again is 1.60 times 10 to the power negative 27 kg. And now I can get rid of this and put this formula on top. We plug in everything, we see what we're going to have. So I'll get this, I'll put it here. Now let's plug in the values. So we have negative half. The mass is 1.60 times 10 raised to the power negative 27. The velocity we have been given. Okay, the velocity we have been given, and we have it there, which is 1200. Okay, so the velocity is 1200, but we square it. I divide this by the charge, 1.6 times 10 to the power negative 12. This should be equal to the linear charge density we have been given is 8.00 times 10 raised to the power 12. I divide this by 2 pi, then in the brackets this is constant, we have said it already, times 10 to the power negative 12 linear final divided by, this is 19. I'm not going to change it to meters because it's a ratio, R final divided by R initial. So the units, even if I leave them as in centimeters, I'm going to have my answer in centimeters. So let's punch now the calculator for the top part here. So negative 1 over 2 is the same as negative 0.5, then times 1.60 exponent negative 27, which is the same as times 10 to the power negative 27 times 1200 squared. I divide this by 1.6 times 10 to the power negative 12. Okay, so what are we getting? So we are saying 0.5 negative 0.5 times 1.6 or 0.5 times 1.67 times 10 to the power negative 27 times 1200 then squared. We divide this by, we're dividing this by 1.6 times 10 raised to the power 19. Okay, so I'm getting 0.0075, which is the same as, I'll just put it in scientific notation. So it's negative 7.51 7.515. I can just say 7.52, I round it off, times 10 to the power negative 3. Okay, this is going to be equal to, now we do this one alone, so that should give us 8.00 times 10 to the power negative 12 divided by, I'll put open brackets, 2 times 8.85 exponent negative 12, then times pi. I close the brackets. So what are we getting? So now I'm getting 0. Here I'm getting 0.144. Okay, I'll just leave it there. Then we have ln RF, then 19 here. So what I'm going to do now here is I'm going to divide both sides by 0.144. Even here 0.144. So what are we going to have? We have -7.52 exponent -3 times 10 to the power -3 divided by 0.144. Okay, so I'm getting -0.052 should be equal to ln RF divided by 19. One thing we should understand here when we're talking about ln natural log is this. Natural log is always in base 10. It's always in base E. So it's like we have this, then you have got 19 is equal to -0.0522. So it is always in base E. So, and we can change now this from log to exponential. So E raised to the power what we have here should be equal to what we have here. Or if you want, you can just take E both sides. You can say, you can put E here, you can also put E there. This and this will cancel. Then you're going to have R final divided by 19 is equal to that. If you don't want to do that, you can say, you can use this property. This is in base E. So it is E raised to the power what is outside is equal to what is inside. So it is, I'll say, E raised to the power -0.0522 is equal to RF divided by 19, like that. Then now you just punch on your calculator, shift where there is ln, that's where E is, then -0.0522. Okay, so it is giving me 0.949 should be equal to RF divided by 19. Then now at this point we can cross multiply. We cross multiply, we'll find that R final will be equal to this times 19, it should be 18.0 centimeters. So that's how close it's going to be. Okay, so in this case we're finding the RF. That's the answer. So it's just a matter of you knowing those three formulas: the formula for the potential energy, which is given by the charge times the voltage, the conservation of energy, and as well as the voltage difference. As simple as that. So when you see any question for infinite, okay, an infinite long line of a charge, just remember this simple principle, see what is missing, then you'll be able to get what is missing. That is it for this one. So we are now on question 4. Question 4 is under superposition principle, and the question is saying, what is the net force on a charge or on charge M in each configuration shown below? The distance R1 is equal to 12.0 centimeters, and R2 is 20 centimeters. And we definitely know that if we convert this to meters, this is going to be 0.12, and this is going to be 0.2 meters. And our goal is to find the net force. Okay. So now for us to find the net force, we have been given three charges, and we want to find the net force on charge A. So let's start with the first part. This is the first part here. Charge A is here. So what we need to know is that we'll start with charge A and B. What's going to happen? So what I'm going to do is I'll say, one thing we have to remember is the electric force is given by the K constant, Q1, Q2 divided by R squared. Now these are supposed to be in modulus because we are just getting the magnitude. Okay, so now in this case we want to find the electric force, okay, of charge A due to B. So we say B due to A. So it's charge. We want to find the net force on A due to B. So it's BA. So it's going to be K, then Q. Which Q are we talking about? Are we talking about QA? So it will be QA, QB, then in the modulus. If you want, you can put the modulus independent, like QA on its own, you put in the modulus. Then you also put QB on the modulus. What I mean is, you put that one, meaning each one has got its own modulus. Then I divide this by the R. So the R is R1 in that case. So you square it. Now, we have been given these charges to be in Coulomb, microcoulomb. So to convert this from microcoulomb to just Coulomb, you do times 10 to the power negative 6. So for example, the first one here, I'll say FBA. Now, these electric force which we're finding here, they are vectors. So we are going to say this. The first part is BA. So A is negative, B is negative. What do we expect? We expect these two guys to repel. Okay, so we expect A to be moving in that direction. So if a vector is moving toward negative x-axis, meaning it's negative definite toward east. So the answer we're going to find here, we're going to include a what? We have to add or it's going toward east, which is positive x. So we're going to add a positive. Okay, so A is going to be repelled by B, so it will be moving toward the east. So let's now plug in the values. What is K? K is a constant. Whenever you are going to be given a test, K is always 9.0 times 10 to the power negative 9. So I'll put K here, 9.0 times 10 to the power negative 9. Then now charge A is negative 5, so I'll just remove negative and put positive because we are just interested in the magnitude. So it will be 5 times 10 to the power negative 6, meaning I've converted from microcoulomb to coulomb. The other one is going to be 3 times 10 to the power negative 6 coulomb. I divide this by R. R1 is 0.12 now squared. So what is our FBA? So if we get our calculator, it's 9.0 exponent neg 9 times 5 exponent 6 times 3 exponent neg 6. I divide this by 0.12 squared. So I'm getting my answer to be, okay, I'm getting my answer. Let me just redo it. We are saying, oh, so this K is not, it's not supposed to be negative. It's just 9. The K value should be 9. Okay, yeah, it's 9. So it is let me just confirm the K value. Let me just confirm the K value. So what is the K value? But it should be 9.0 times 10 to the power 9. Okay, yeah, it's 9.0 times 10, 8.99, or 9.0 times 10 to the power 9. And the SI units are meter squared per coulomb squared, like that. Okay, I've confirmed. So this is supposed to be just a positive 9. So 9.0 times 10 to the power 9 times 5 times 10 to the power negative 6 times 3 times 10 to the power negative 6. I'm getting 0.135. Divide this by 0.12 squared. Okay, cool. So the answer I'm getting now, since it is going toward positive, I'll say it is positive 9.375. It is a force, so it is in Newton. Okay, then now we go to the second one. So the second one is going to be the electric force of A due to C, so it is CA. It will be K, then K QA QC R2 squared. So we have FCA, the K is 9.0 times 10 to the power 9. Then this one now, A is the same, 5 times 10 to the power negative 6. The other one is also going to be 3 times 10 to the power negative 6. Because we are interested in the magnitude, the negative you ignore it. So R2 is now 0.2 squared. So what will be our FCA? So we'll have 9.0 times 10 to the power 9 times 5 times 10 to the power negative 6 times 3, then times 10 to the power negative 6. I divide this by 0.2 squared. So it is 3.375 Newton. Now let's check. So this is negative and that is positive. So what do we expect? So charge A and A, what do we expect to A? A is negative, so A is going to be attracted to C. So we expect our net force, or our A, to be attracted there. So A will be moving toward the negative side. So therefore you include negative there. So now we want to find the net force. So you say the net force is going to be, we add now FBA plus FCA. So what is FBA? FBA is positive 9.375 plus what is FCA? Negative 3.375, like that. So we expect our net force in this case to be, our net force to be 9.375 to be 6. So it's positive 6 newtons. That's the net force. So it is going, since it is positive, meaning the net force is moving toward positive x-axis. Okay, so that is it for part A. Now if we go to part B, you can pause the video, use the same principle which we have just used on part A, and find the answers for part B. So let's go ahead and find part B. So we are trying to find, first we have to find, it's the same thing, FBA, we'll have K, QA, QB, then R1 squared. K is a constant, 9.0 times 10 to the power is 9. Then QA is the same, so 5 times 10 to the power negative 6. Again, this one we have B. Where is B? It's the same, so I'll just ignore the negative like we said earlier. Now the R, from here the R is the same, 0. The R is 0.12 squared. So now so we'll have this. Isn't it going to be the same as the first one we had? It's going to be the same, 9.0 times 10 to the power 9 times 5 times 3 like that, divided by 0.15 squared. Now I'm getting the answer to be 9.375 newtons. Now let's see the sign. So we are interested in A and B. So this is negative, that is negative. What do we expect? This guy is going to repel. It's going to be repelled. So A will be repelled and A will be moving in that direction. Okay? A will be moving in that direction. That direction is positive. Next, we go to the next one, which is A and D, that other one. So even this one is going to be the same. Definitely it's going to be the same. So we'll have F, okay, we'll have FB, or we'll have FCM. The K is 9.8, 9.0 times 10 to the power 9. Then my A is 5 times 10 to the power negative 6. My B, in that case C now, 3 times 10 to the power negative 6, like that. We divide that by, we are dividing it by R2 is 0.2. Now we square it. We'll get the same thing, I think, because this is what we had previous. So we'll get 3.375. Now, is it going to be positive or negative? Let's see. So this is negative and that is positive. What do we expect? So this is going to be repelled. So since it's going to be attracted, sorry. So it's not going to be the same. A is going to be attracted to C. So it will go in that direction. So this will be positive. So the net force is the summation of FBA. This is supposed to be FBA plus FCA, which is 9.375 plus 3.375. So the net force will be 3.375. Okay, so we have 9.375 plus 3.375. So we'll get the net force to be positive 12.75 newtons, like that. So the net force will be going toward positive side, positive x-axis, to moving toward positive x-axis, and the answer will be 12.75 newtons. As simple as that.